In this video, we will talk about electrochemical cells. There are two main types of electrochemical cells. There are voltaic cells, which are also known as galvanic cells, and there are electrolytic cells. The main difference between these two different electrochemical cells are the spontaneity. Galvanic cells are spontaneous, whereas electrolytic cells are not spontaneous. Electrolytic cells require an electric current to be passed through in order to drive a chemical reaction that would otherwise not occur. Galvanic cells happen spontaneously, and so they will generate an electric current that can then be used to power electronic devices. So batteries run on this power. Batteries run on this way. So you can separate the different half reactions into different parts of the cell in order to force electric current through a particular path in order to complete the circuit. What's common in both types of cells is where oxidation and reduction occur. In both cells, oxidation occurs at the anode. So oxidation occurs at the anode and reduction occurs at the cathode. How you can remember this is oxidation and anode both start with vowels. And then reduction and cathode both start with consonants. I'm really paranoid about my spelling right now. But C and R are both consonants and A and O are both vowels. And I'm not sure if I spelled anything correctly. So batteries are voltaic cells. I started getting into this on the previous slide, but any type of battery is a galvanic cell or a voltaic cell. Same thing. So all those car batteries, alkaline batteries, cell phone batteries, which are lithium-ion batteries, nickel-cadmium batteries. There's different chemical reactions that you can have to power your battery, and the voltage really depends on which items you select to put in your battery. So if you want a high voltage battery, then you're going to pick metals that are far away from each other on the activity series, and a low voltage battery would combine metals they're closer together on the activity series. Because that distance that they are apart on the activity series relates to the electric potential you'll get out of the chemical reaction. So we got to put the electrons to work. Electricity is the movement of charge. And so it's written right there. Electricity is caused by the electrons moving between the atoms. And so we have to force our electrons, instead of just happening together in a beaker, we got to force our electrons to go on a much longer path to power our electronic device. And so in the middle of this pathway, you can put like a light bulb. This is a badly drawn light bulb. Old school incandescent bulb. So this was our zinc and our copper solution that you might remember from a previous video. And so we can split this into two different half reactions and put them in separate beakers. And so our reduction, that's our oxidation half reaction and our reduction half reaction. And now instead of allowing them to occur in the same beaker, we're going to separate them. And so we have, in this part, we have copper as a cathode. Cathode is where reduction occurs. And then we have zinc as the anode, and anodes are where oxidation occurs. And so we've separated the cells so that we can have our zinc anode come out into solution and become zinc aqueous ions. And then our copper will flow and become copper solid as this reaction occurs. Now, we know that we have to have these two electrons travel all the way. These two electrons where the zinc loses will travel up through the anode, down through the wire until they reach here, at which point the copper ions will grab onto them and plate onto the surface. Now, to complete the circuit, we have to remain charge balanced, and that's where the salt bridge comes into play. So as we are using up the copper ions and turning them into copper solid, we are using up positively charged ions. And so in the salt bridge, there's salts that are not really participating in the reaction, but the positive charges will flow this direction to replenish more positively charged ions, and the negatively charged ions will flow the other direction because over here we're generating more positive charges, and so we'll need more negative ions in order to charge balance that beaker out. And so the salt bridge ensures that we are keeping both of these beakers neutral overall. So this completes the circuit with this movement of electrons. Electrolytic cells require energy input. And so we have a battery, and it's going to drive a chemical reaction that would otherwise not occur. This is used to plate objects and plate jewelry and silverware and whatnot with the metal. And so whatever you want to plate, you can turn into the cathode. And so you want it to turn it into the cathode because at the cathode, reduction occurs. And at the anode, oxidation occurs. And so we want the silver here to turn into ions and lose an electron. And then we want that silver to turn back into silver solid once it reaches the surface of our cathode. And then we'll coat that entire spoon with silver. Our electrolytic cell, though, requires energy input. So our electron actually travels this way. Through here, and then the silver grabs back onto it. Okay. So this reaction otherwise would not occur without that battery there to drive the reaction. You can do your own redox reaction at home. This is a chemistry life hack for cleaning tarnished silver. You might have some silver jewelry at home, or have like some actual silver coins or something. And so this is how you can turn it from a corroded, tarnished silver back into a shiny silver. This was a made-for-TV product that's completely useless. This is just a sheet of aluminum. And so you don't need to actually buy the sheet of aluminum. You can use aluminum foil. Aluminum foil works just as well. So what you do is first you have to understand what that tarnished substance is. That tarnished substance comes from silver metal reacting with hydrogen sulfide gas. This is from like farts. This is from the methane gas in your stove. They lace the methane gas from your stove with H2S. Smells like rotten eggs. So that smell that you associate with natural gas, that's actually H2S. And it's also found in farts. But that's going to react with the silver metal to produce H2 or silver sulfide and H2 gas. This reaction happens naturally. That's the spontaneous direction for that reaction. And so you don't actually notice the H2 gas being formed, but eventually you end up with H2S all over the surface. And so what we're going to do is we're going to turn that H2S back into silver metal. And we're going to do that by turning our aluminum into aluminum sulfide. So we can see here that we're going to turn our Ag plus into Ag neutral and our aluminum neutral into aluminum 3+. And so we have our oxidation half and we have our reduction half. And so what we need is we need our aluminum solid in a bowl. Use a glass bowl, not another metal bowl. You don't want to risk accidentally oxidizing your metal bowl instead of reducing the silver. So line a glass bowl or something with the aluminum foil, fill it with water. That's going to act as your medium for the electrons to flow. You should lace your water with table salt or baking soda, which is sodium hydrogen carbonate. And that's your ionic compounds to make ions that help complete the circuit and move electrons. Conduct that electricity through your water. And so as soon as you have your salty water, you should use boiling water. That works a lot better. And then you put in your silver object, and as soon as your silver object touches the aluminum foil, then it becomes much cleaner. You might want to scrub it with a soft toothbrush while it's under there to make sure that you're loosening all that debris, and it will come off very easily.